Hello, everybody. This is the P1B session, a real world application one. Welcome. Today we have 5 talks. And let's get into it. This actually is a really cool mixed session with both long papers and industry talk. So let's get started with the first talk, which is goal-driven command recommendation for analysts. And this is going to be presented by Bhanu, Prakash, Reddy, Guda. He's a research scientist at Adobe Research in Bangalore, India. Okay. Please go ahead, Bhanu.
I'm audible. Hello, everyone. I'm Bhanu Prakash from Adobe Research, and I'll be talking about goal-driven command recommendations for analysts. With the volume of data increasing day by day, the capabilities to support the processing of this data are advancing a lot, and the analyst whose task is to analyze this data need to make several decisions within the softwares, whatever they are using to achieve their goals. Considering the volume to be analyzed, there is a demand for the systems to quickly analyze and draw inferences with a low latency. So this demand carries over to these analysts who are assigned with their task. So this brings us to the question, how do we guide the analysts with their workflows based on their goals? So we can see that this question itself is a very wide area of interest. And we try to solve it to some extent using next step recommendation models. Our solution is to provide a recommender system. A recommender system acts as a primary filter to rule out the options that are completely irrelevant to some extent. The model that is learned from the users who are already familiar with the software and have been performing the tasks on that application can act as a guide for a novice user who doesn't have any experience on the platform. So our objectives for such a recommender system are the following. We need to improve the performance of the recommender system with the help of goal information. And we provide the recommendation. We should provide the recommendations that should be that are relevant to the analyst's goal. And we should be able to steer the recommendations whenever the analyst is deviating away from the goal that is specified. Let's have a look at some of the prior art. There is a vast amount of literature related to the concept of goals in process mining, web mining, education, and HCI. The Lumiere project by Microsoft defines a goal as set of target tasks or subtasks at the focus of users' attention. Note that we are using the notion of task and goal interchangeably here. Here are a couple of recent works. The first one is unraveling and learning workflow models from interleaved event logs. So in this work, they have used probabilistic suffix keys to model workflows. And also they have used topic modeling to identify the tasks or workflows. The second work is a previous work from us where we have proposed a neural network architecture where we predict the next command in a sequence that is aligned with the task. We differentiate from these works by making the recommendations more goal-oriented with explicit signals of the goal through inputs and loss function. Here is an overall workflow of an approach. This is the workspace that is available to the analyst. And here is the extension that we have built using our models. We provide the goals that are available in that application. So now the user chooses his or her goal for the session. And after choosing the goal, as soon as the user starts performing the actions, they get their insights, and in parallel, we'll be providing the recommendations for the analyst. So here is the picture of the entire backend components together. Before going through each one of these, we'll go through the data set first. So the application which we are considering here is a web analytics system. The recommendations we are providing are the options or clicks that are present in the software. So the data set we deal with is the user interface click, and we denote a command or an action as a click that is registered in the log data when the user clicks in the interface of that system. And we categorize the interface clicks into two categories, the software commands and data commands. If we look at the examples from a spreadsheet application, we can see the difference between the two sets of the commands. So the software commands are something that facilitate the data analysis, but on the other hand, the insights that the analysts are trying to get are actually closely related to the data. So out of these two commands, we'd like to predict the data commands. Since we are predicting only the data commands for the sequence, so if we look at an example here, for this sequence, the data command that needs to be predicted is the one that is highlighted in the board. Um, so let's have a look at how we identify the goals. So we leverage unsupervised approaches from the prior art to solve this problem. We treat the sessions as the documents and commands as the words and goals as the topics and apply the topic modeling. We use ByTerm topic model because it is suitable for short text, and in our cases, it's uh, short sequences of sessions. And for fixing the number of goals, we use the popular measures, which are UCI and UMass. The objective of both the measures is that the commands that belong to a goal should be close to each other, and the goals themselves should be far apart from each other. And for getting a human readable annotations for these goals, we did it through human annotation. And now that we have the goals in our hand, let's see how do we incorporate this information into the models. The first approach we have tried is a ensemble approach. So here we try to segregate the data into different goals based on the output that we are getting from the ByTerm topic model. So after segregating the data into respective goals, we learn one model per goal. The architecture of this model is shown here. We feed the commands to the LSTM models using the learned embeddings, and we predict the next command in the sequence using the last hidden output. As we can see here, we have one model per goal. So in such cases, the models will not see examples which are not belonging to that goal. So we have tried the other method where we explicitly mention the goal information along with the sequence so that we can have a one single global model. So we concatenate at different layers that are possible in the network, and we have tried all possible combinations, all possible input information. And these are the baselines that do not have any goal information. These are the standard baselines in recommendation models. And these ones are, we tried the ensemble approach on the baselines. And these are the approaches which we have tried by inputting the goal information into the models. And we can see that the performance improves by a huge margin. And also, if we look into the goal-wise accuracy results, we see that our model is performing best in all the cases. We'll talk about the fine-tuned model here in the upcoming slides. So let's look at the custom loss function we have come up with. So the proposed models till now are using standard cross-entropy loss. This loss makes sure that the recommendations are aligned with the input sequence, but they do not consider whether the command that is being predicted is relevant to the specified goal or not. So we introduce a component which is containing the goal information. So we have already the probability distribution from the ByTerm topic model, which gives the probability distribution of observing some certain data commands in a goal. We need to measure how much the predicted distribution of commands is deviating from this distribution. So we use the K and divergence loss. Finally, we use a weighted loss function between these two losses. And so if we look at the component Q in the KL divergence, it is different for different goals. So eventually we have to learn one model per goal. like in the Ensemble approach. But to overcome the problem of generalizability, what we do is we first retrain the models on all the data with the cross-entropy loss, and then fine-tune with the balanced loss function. Using this, we get both accurate and goal-relevant outputs. And also an advantage that we get with this approach is we get superior performances for low resource goals as well. These are the results which we have seen earlier, and as we can see, as we have already observed, it's having significant improvement. But this measure of standard test accuracy does not convey how well we are performing in terms of the recommendations being goal-oriented. So we propose a new measure to evaluate the goal orientation, which we call as geo measure. The first term here is the accuracy, and the second term is the byte topic model command distribution probabilities. And we balance both of them by using the formula which is similar to F1 score. So as expected, the GO1 value is higher for the models with goal information. After fine-tuning, we see a sharp increase in the GO1 measure because of the importance of the loss function and the fine-tuning approaches. And this performance is consistent across all the goals. So it is often possible that the user might deviate from the specified goal. So we wanted to test our performance in such cases, how our recommendations will be. So we simulated an experiment where we take a model and we give, which is trained for a specific goal, and we give input sequences from the other goals. As expected, there is a decrease in accuracy because of the goal orientation component in the loss function. But if we take the goal orientation score, which is combination of both accuracy and goal orientation, it's still intact. And this is consistent across the different goals. So concluding, we conceptualize the notion of goal in software application, data analytics application, and we have investigated the effectiveness of incorporating goal information while recommending commands. And we have designed custom loss functions and also experimented with fine-tuning approach to tailor the data commands for the specified goals. And we have also proposed a novel evaluation method, which is the GO1 measure. Also, in future, we'd like to explore the recent advances in attention and transfer learning mechanisms. We'll also experiment with more sophisticated models to predict the user's goal in real time as the session progresses, which we are currently asking from the user as an input. And we would also like to handle the problem of noise user misspecifying the goal, thereby giving better recommendations. Thank you, and I'd like to answer any questions.
Yeah, thanks for the presentation. Let me ask some questions myself first. I did not see any live Q&A come in for the session. One is actually a good question from the morning that I'm wondering if you could elaborate a bit. Where do these goals come from? Can you give us some more examples of that?
Yeah, so we have used the unsupervised approaches from the command so software clicks. So eventually we will not get any labels from such models such as the topic modeling. So we have asked the product managers who are the experts in this application. So they have looked into the clusters that we have identified, and they came up with some names. For example, product analysis in campaign, or segment analysis for campaigning research, or search trends for campaigning research, etc. These are some of the goals that we have in our application. But it might vary for different applications. Like if you go for Adobe Photoshop, or if we go for Adobe campaign or something like that, the goals might vary depending upon why particular users want to use that software.
I see. Okay. Next question is around data. What is segregation data? And one, could somebody say that's segregation data? And maybe you can also talk about your training data.
Yeah. So data segregation is actually, we have done it because one of the ways in which we can tell the model about the goal is through data itself. For example, we can say that this particular session is this is belonging to this goal implicitly by separating each of the sessions into their respective goals. So for that, we have used the Byton topic model's output. So Byton topic model gives a probability distribution of a session belonging to different goals. We take the top probability there and we assign that session to that particular goal. So that is one method in which we wanted to incorporate the goal information into the models.
I see, thank you. What about training data? Do you then, for all of your positive examples, you always put a goal to it?
Yes. So for each of the sessions, there is no positive and negative training examples here. So we have the session and we need to predict the next command in the sequence. So for each of these training sequences, we have an assigned goal that is identified by the topic model.
I see. Okay. And then if, like you said, if the goal actually changes or the person changes their goal in the mid, then you're still working on that part to solve that.
Yes, we are working on that part.
Okay. Thanks very much. I think those are all the questions. Let's go to the second talk. The second talk is SSE-PT, Sequential Recommendation via Personalized Transformer. And Liwei Wu is going to be our presenter. Please go ahead, Liwei. And he's a student from UC Davis. Oh, actually.
Oh, sorry, I think I was muted. Is it good now? Okay, so yeah, hey everyone.
Yes, we can hear you.
Okay. Hey everyone, my name is Liwei, and so this is joint work with my course Shuqing, Cho, and James. So let's first talk about what is secure recommendation. So secure recommendation, so traditionally the recommend system usually takes ratings or rating pairs as input, and then the time component usually is used as a feature. But in secure recommendation, we actually are giving the item sequence that each user engaged in temporarily as input. So in the example below, so if one user has watched a series of movies, the goal of the problem is want to predict the next movie the user is going to watch. So if we write it down in a mathematical format, then the input are actually as SI. So SI is the input sequence for the ith user, and I is from 1 to n. And then we can write the form as JI1 to JI2 and JIT, and T is the number of timestamp here. So here the sequence is of length T. And the goal is when you predict the next item, given the user's previous engagement history. So if you look at this example, the item sequence actually has a lot of similarity with word sequence in NLP. So each item sequence can be thought of as a sentence in natural language. So no wonder so many previous words have actually borrowed techniques from transformer model on the left or the bottom model on the right to this particular problem in recommend system. So if you are familiar with transform model, it's basically a self-attention model. And And then the better model is an improvement upon the transform model, but making the model bidirectional. So the first paper adapting transform model to this problem is called SSRec, and so it's very similar to transform model. But when you directly use the transform model in this problem, actually there's some issues. First, because the recommended system actually is inherently very different from NLP problem. So we usually care more about personalization, but in NLP, because there's no user concept, so the only embedding use is a word embedding. But here, if you only use item embedding, we realize that there will be a lack of personalization. So the paper argues that the transform model is expressive enough such that the user embeddings are not needed. And in this talk, I want to argue that's not the case. Similarly, but for red model also needs the personalization component. So then we go back to this problem. So why it's very hard to add the personalization to SSRec, for example? So the issue is because if you have n sequence and if you naively introduce n k-dimensional user embedding, you have a lot of more parameters, but the data is very limited. So this unfortunately leads to overfitting. So we find that existing regressing techniques such as dropout, weight decay, or parameter sharing are not sufficient enough to reduce overfitting. So to solve this, so we did a simple experiment by just adding the user embedding. Then we realized the performance dropped a lot from the SSRec. And then if you add the parameter sharing, the performance gets a little bit better. And then if you add L2 and drop out, the performance gets slightly even better. But they're not sufficient enough to beat the performance of SSRec. So that's why we propose a new regression technique called SSE-PT, and this will help us to overcome overfitting and being able to add the personalization component in the model. So what is SSE? SSE is called stochastic sharing embedding. So we proposed this method in the Neurops last year. So the main idea is that usually when you do an embedding lookup, in the training time and test time, you will get exactly the same embedding I if you're doing an embedding lookup for the I embedding. But we modify the training procedure a little bit. So when you cover embedding I in training time, we actually have some probability that we'll master embedding I and transition into embedding I prime. And this probability is defined that when the embedding I and embedding I prime are related, then the probability of transitioning should be higher. And this way, you actually will, when you do an embedding lookup in training time, you actually will get different embeddings, and this will help you reduce overfitting. And we in the paper, you can find more details. We also show that it actually smoothing the loss surface, so it actually makes the function converge also faster. So with the help of SSE, we actually being able to add the user embedding. So we add the user embedding in this way. We concatenate with item embedding before fitting into the transform model. And also in the output layer, we also add the user embedding. So the output of the transform model, we are doing a dot product with the positive item and negative item. And then we are using a cross entropy loss scheme. So with this new architecture, we realized that this will actually significantly change how the tension map behave. So for this example, movie length 1 million example, so one user watch a bunch of movies, and then we want to predict the next movie. This user want to watch next. So if you look at the recent movie the user has watched, actually there are a lot of Shakespeare movies. So it's no wonder that the user actually will also watch another Shakespeare movie drama as the next item. But if you are doing SSRec recommendation, actually the model won't be able to capture that. So because the attention map actually are scattered over the sequence, because in NLP there's no need to emphasize the recent item. So the attention usually is scattered around the sequence. But if we add the user embedding, actually the model will be able to capture that the user actually recently watched a bunch of Shakespeare movie. For example, 41, 31, 36, 33, they are all very highlighted, and the model is able to capture that part of information. So that also makes our quantitative results much better. So when we compare results from, for example, with non-deep-learning methods, our results is much better. And we also compare with deep learning methods such as the GRU for REC, and also other CNN-based method or SSRF, which is transform-based method. Our results is significantly better. We also showed some ablation studies. So basically, if you reduce user embedding, the results actually gets worse. And also, if you improve the length of the sequence, actually the longer of the sequence you use, the better results are. And you don't have to use the same dimensionality for user and item. So you can use 50 for user and 100 for item in this scenario. We also show that the training speed of our method is actually faster than SSRF, just because our convergence speed is actually faster. So the conclusion here is we propose a novel architecture called SSE-PT for the sequential recommendation problem. And the SSE-PT enjoys benefits of being a personalized model. So therefore, this achieve better results than current state of art models. We demonstrate that the importance of SSE realization for incorporating user invariance, and we argue that when one adapts another NLP model to recommend system setting, probably you should also include user invariance for better personalization. So our code is also open source on GitHub. Yeah, that's all for my talk. Thank you. Sorry, I think you are muted.
Sorry. Thank you, Liwei. So again, I don't see any live question being asked, so I'm going to start asking some questions that I thought is interesting from the morning session. Mm-hmm. Maybe you can answer here, but I mean, super interesting talk and fairly new direction as well. So one question is around the really around the practicality of training for sequential recommender in general. This is around like, how do you see input sequences being fed back into the trainer at real time, and how do you see that update since you're proposing this user embedding?
Yeah, actually that question, I wasn't very sure that is that what's the bottleneck when you're serving the model online, or what is the problem?
Right, yeah, just how you see if you need to retrain all of your sequences and then you have new sequences from user, how do you see that to scale?
I think this model can be retrained, or you can just refresh every day. So if user has a new longer sequence, we just need to shift the truncated sequence slightly different, and then you can keep the same user embedding, and then retrain on these new sequences, and if you have too many users, then you can also maybe hash the user IDs, so you don't have to keep unique embedding for each user. Yeah, and And I think this can be retrained each day. I mean, but maybe the bottleneck is the length of the sequence. If the sequence is too long, then we also want to I mean, avoid that. So that's the open-ended problem. So how to deal with long sequences? Yeah.
Yeah, that makes sense. And there is a live question kind of following up on that. If you could elaborate on the runtime and if this is scalable, could you make comments on the scalability?
Yeah, I mean the time complexity is pretty much the same as SREC, right? I mean we only added the user embedding, so so you may see slightly increase in training time, but because the model is faster to convert, so I think as shown in the plot, the wall time actually they're pretty similar.
Yeah, so I see another question that's quite interesting is, do you also consider the time each interaction happen in the sequence? Meaning that, do you have a sense of how the gap between two events in the sequence?
I guess I don't kind of follow the question. So what do you mean by two events in the same sequence?
Like each of users' interaction. For example, if you consider a session several user interactions, right? And some of the interactions could have happened maybe an hour apart. Some could happen 2 minutes apart. So I guess the question is, do you consider the time difference between the interactions?
Yeah, that's a very good question. I have thought of this before, but simply in literature, people usually don't consider that. So usually, you just giving the sequence without actually thinking how much gap there between the two items. I think that's definitely an interesting question to follow up in real world. Like just because it doesn't make sense to think what sequence are should be equal weighted, right? Because if some are very far away, then maybe that shouldn't be treated the same as the two adjacent items the user has engaged in the same day.
Right. So future work.
Yeah.
All right. So the next question is, in GRU for Rec, the authors propose data augmentation by splitting the training sessions. Could that be used to avoid retraining the model? This is kind of going back to the retraining.
Yeah, but what we find actually is always we actually in our paper we propose SSE-PT++, but that's basically essentially what is suggested. So we split the longer sequence into small shorter sequence, and we actually sample them in a different weight. So we try to sample more heavily on the recent sequences, but even by doing that, we find that the performance, I mean, it's not as good as you directly using a long sequence. I guess the reason is we use fewer parameters when you use shorter sequence. So that's so if we are limited by the model size of transform model, so we have to shorten the sequence somehow. But even if when I try to do the sample them differently, still the results is not as ideal as they are probably supposed to be. So I think that's also open-ended question. That's for future work, just how to deal with the super long sequences. For me, it seems chopping them down and sampling them differently is not the best way to do it. Even though I did it in the paper.
Right. That's great. So let me ask another follow-up, not a follow-up question, but just another question in a different topic. So we have a question about, would missing elements in the input sequence affect the proposal? Sometimes it's not possible to detect all the elements.
Actually, for each user, we don't assume they're always equal lengths. So we just pad zeros to the left if they are not long enough, and you mask them, basically mask them in the training stage, so they don't get trained for that part. I think that works for us. So that means that yeah, we don't consider each user has to be that long, but it still encourage use a long model. So for us, remember for one data set, the average length is only like maybe 20, 30. But still you want to use a maximum length of 50 or 100, just because the longer usually the data is very long tail. So even though average length is like 30, 40, there are still some users has a very long sequences, and you still want them to be captured by the model. So I would encourage use the maximum length to be as large as possible as you can afford it, and then when you once you reach the limit, then you should think about how can you scale them up, and without losing the performance.
Right. Okay, that's cool. That's a good answer. I'm gonna do one last question around the context. Do you consider the time of day the movie was watched, and other time or other context?
Yeah, that's very good. That's another very good future direction, actually. Just because here we don't consider the set information of the movie, but I think for me, I think you can definitely add the set information in the model somehow. Like, I mean, because the loss can be slightly modified or something, or you concatenate with the features. Yeah, but we think using the additional information about the movies will definitely help the performance. But just because in literature usually people don't do that, and then for fair comparison, we also don't add the set information. Yeah, just because it's orthogonal to our work. The main takeaway for this work actually is to make the model personalized and argue that when one adapts the NLP model to recommend system, you shouldn't just do it directly. Just because the recommend system is very unique in the sense that we have users and want our model personalized for each user, but NLP model usually don't handle that very well.
Makes sense. Okay. Yeah. Thank you. Thanks very much, Liwei. Let's thank our speaker, and then this is the time when you applaud, audience. The only thing we don't get on this virtual platform. Okay, so the next talk is an industry talk. So this is about developing recommendation system to provide a personalized learning experience at Chegg. And this is brought to us by Sanhamitra Deb, and she is at Chegg.
Hello, everyone. Very excited to speak at RecSys for the second time. Today, I'm mainly going to talk about how we develop a personalized learning experience for students at Chegg. Let me briefly take you through the outline of the talk. I will initially talk about what we mean by recommendations of Chegg, and then go into organizing content into a knowledge graph, and do a deep dive into content classifications and talk about cross-product recommendations at the end, and leave you with some takeaways. So what do we mean by recommendations at Chegg? The main goal of Chegg is when a student comes to the platform, we want to make sure that the student is getting the right content shown to them so that it improves their learning experience to the maximum extent. In order to do this, we organize our content into a knowledge graph, and then we detect user patterns and show content that is relevant to specific users. Let me go a little deeper into this. So Chegg is a centralized student platform where students come in and get a range of services. There is textbook rentals, question answering, online tutoring, flashcards, writing, math solver, and many other products. So here I have like a screenshot of one particular product, which is textbook solutions. And based on this student's activity, we know that the student is studying engineering mechanics, and we make a bunch of suggestions to study questions from different chapters of the book. We also know the student is studying chemistry, and we make several suggestions in that space as well. And as you see, like both of these have drop-down arrows. So if in case we get it wrong, the student can use the drop-down arrow and change the subject. So this is like the form of recommendations that we want to provide at Check. Now, this is a good point to segue into the knowledge graph. So our main, like the backbone of our personalizing experience is a knowledge graph where we organize our content into this hierarchy of subjects, and each subjects have a bunch of courses. Courses have a bunch of concepts, and then concepts have some sub-concepts. We get these nodes given to us by subject matter experts, and these get constantly iterated as more subjects become important or new concepts are taught. One example of this is physics. You have several courses in physics like electricity and magnetism, mechanics, quantum physics, and then mechanics has several topics like acceleration, velocity, displacement, etc. Now, the important part is like the first part is creating edges between the content that we have and the different nodes in the knowledge graph. I also wanted to use the slide to give you a sense of what our content looks like. So for question answering, you typically have like some form of question. This is a question in physics. For flashcards, you have front of the card, which is very often some kind of term, and then the definition for the term could be the back of the card. For textbook rentals, you can go in and see a collection of textbooks and rent from them. And in writing tools, typically students upload essays and get different types of helps. It could be like grammar checks or developing citations and other forms. Now, in order to connect this content to the nodes of the knowledge graph, we use machine learning classifiers. And I will do a deep dive into classification a little later. But the next step is to connect users to the nodes of the knowledge graph. And we do this through the interaction of the users in different sites. Here I have given this example of the first user who has studied this particular question in physics and also rented this book in physics. So we conclude that the student is studying physics, and based on the interaction with different topics, we conclude that the student is studying acceleration. So based on this, now when the student goes into flashcards or writing tools, we can make very relevant suggestions in acceleration, or do you need help with your physics paper? So now I will do like a little bit of a deep dive into the content classification pipeline, which basically connects all our content to the nodes in the knowledge graph. So the first step is text pre-processing, and this is very important because it removes all of the noise, or most of the noise in the data. There are a lot of rules here, some very specific to Check, like we get words like chapter or study or such words very often which do not help with classification, and we remove them. The next phase is a very important phase of any classification pipeline, and it has to deal with collection of training data. So it's important to make sure that you have a good annotation pipeline in place, because your model performance will directly depend on how good this is. And we use two sources, one of which is subject matter experts tag our content with different nodes, but we also get feedback from students. We ask students, what course are you studying right now? Or rather, we ask students what course this piece of content belongs to. And it's usually optional, so not all students give us that feedback. And once we have that data, the next phase is model building, and I'll do a deep dive on that. And finally, the final phase is model evaluation. The first phase in the evaluation is offline evaluation. And depending on how the model is used, we sometimes have high precision, low coverage models, because for that particular product, you just don't need a tag for all the content, but you need very high quality tags for the content. And then in other products where, the precision is not so important, it would typically be like a high recall model where, you catch everything and give the output in that way. And then finally, this is deployed online to see, how well students accept these recommendations in some sense, or if you're recommending a content in a topic, does the student accept? So now I will go into one of the classification problems. I have shown different stages of the knowledge graph. There was subject, course, topics, and terms. And I will go at course level. The reason I choose course level is because we have a good amount of training data on courses, because we are able to collect better training data for courses from students and also from SMEs. But the courses are also not as, in some sense, they are more difficult than identifying subjects because there are several thousands of courses and it is more granular and with overlapping concepts in some sense. So modeling approaches. The first modeling approach that I typically use is use TF-IDF features with some kind of a classifier like an SVM or a logistic regression. And I generally work on this while training data is getting collected because this kind of gives you a sense of how good your data is. What do the results look like? The main cons of this model is that it does not do well for subjects dominated by symbols or raw text, and it will do well if you include like character and words in your features, but that makes the model really large. So we turn to deep learning, and basically I use character-based CNN for this purpose. The nice thing about this is that you can use out-of-vocabulary words. This makes it particularly suitable for raw text or for multiple languages. The nice thing is the model is very small. It can have a maximum of 70 characters. This makes deployments really easier. The API will, return a result in like 150 milliseconds or something like that. And that makes this model basically usable in multiple products within the company. And last but not the least, convolution and pooling layers are really good at picking up local cues. So it's really good at picking up phrases that might be directly correlated in some courses. Now I will go into the architecture of the model. And it's a fairly standard architecture in some sense for classification. We have some text data, which is quantized, and then we apply 2 layers of convolution and pooling. And then after that, we have a dense layer, a dropout, a ReLU, and a norm. And this is a normalization, and this is like the basic architecture. Using this architecture, we optimize for 2 different tasks. And the reason we optimize for 2 different tasks is that the front of the card and the back of the card is a data that we get for free. And I think I probably did not mention this, that this whole problem is assigning courses to DEX, which is a collection of flashcards. So these are flashcards that students use to study front of the card and back of the card. So this is like one data that we just directly get for free. And that's one task we optimize for. So given the front of the card, predict the back of the card. And the other one is the training data that we have for classification. And we optimize these 2 simultaneously to get the results for classification. And here is a little bit about model performance. This has 73% accuracy on offline test data. It's measured at top 3 because sometimes courses are overlapping. Like we have courses like intermediate microbiology and introduction to microbiology. Overall, the challenges in this problem is imbalanced training data. So for some classes, we have too few training examples. And one of the reasons this happens is because some courses are just not as popular. So not as many students use the data and not as many students give us feedback. So we are in the process of collecting more training data in classes that are less used. And we're also looking into rule-based techniques to augment the training data. And finally, I would like to say a little bit about cross-product recommendations. So we face this cold start problem where very often a student would use one product, such as Check Study, and then browse through some other products, but not really use them much. And it's very important to surface relevant content in these other products for the students to understand the value of those products. So the way we do it is we use content filtering in some sense. So from the knowledge graph, we know that this student is taking this course, studying these concepts, and they may be in one particular product. And we recommend the most trending content in that course in a different product. The other thing we use is text-based similarity, where based on content engagement on one product, we would show similar content in another product. And we mix and match these up depending on how much user data we have. And finally, since I'm nearly out of time, I will leave you with some takeaways, which is pretty much the summary of what I've said so far.
Okay, thank you, Sancheti. Thanks for the interesting talk. So I'm just going to ask the one question since we are a bit out of time. I'm wondering, so actually this was a question that asked if there was some A/B testing that you have seen that CNN does much better than your SVM model, and if how much?
So we have not done A/B testing, but we have done offline testing where we've seen that the CNN has performed better by a few %. But the few % gain was not the only reason to deploy this model. The main reason to deploy the model was the lightweightness of this model. So the TF-IDF plus SVM or logistic regression, it was a much slower model. Mm-hmm. And we needed something that was really fast. Now it's possible that there can be another model which gives us more gain and also has comparable speed. But the main reason we chose this was speed and some improvement in accuracy.
Great. Thank you so much. Thanks for the great talk. Okay, so let's go to the next talk. It's also an industry talk. This is the behavior-based popularity ranking on Amazon Video, and this is going to be presented by Lakshmi Ramachandra at Amazon.
Hey.
Please go ahead.
Thank you for that. So hi, everybody. My name is Lakshmi, and I'm an applied scientist at Amazon Search. And I'd be discussing my work on developing behavior-based popularity models to rank videos on Amazon. Oops. Okay. So when customers use video streaming services, they use predominantly two approaches to find content. The first mode is discovery, where when they're on the landing page, they're presented with these carousels of videos that they can sort of scroll through or page through and then find a video that they're interested in watching, click on it, and stream it. And the other mode is through search. So you go to the search box, click there, type the name of the movie or the TV show, and then select it from the result and then start streaming. Now, on Amazon Video, discovery actually accounts for over 70% of the traffic. So it's a really large part of Amazon Video. So there's a lot of effort to improve customer experience in the discovery mode. Now, in the discovery mode, unlike in the keyword search world, there is no explicit sort of user intent that's specified in the form of say a query, right? Like in the keyword search world, customers specify what movie or TV show they're interested in watching. So you have some sense of context at that point. Whereas with discovery, there is no such context. And to add to that, there are also challenges posed by scale. So Amazon Video is huge. The catalog is really large. It has a variety of content types, which include movies, TV shows, live sports, channel subscriptions. So building a model that basically addresses all of these different use cases becomes a challenge. Apart from that, there's also a challenge with surfacing new and original content, right? Like you want to provide fresh content to customers so they can quickly sort of like explore new videos that are available. So this is also a challenge with discovery. Now, in this talk, I'll sort of be focusing on popularity, predicting popularity of videos. Now, historically, we've relied on heuristics to identify whether videos are popular or not. And this may include things like, the number of clicks a video is received, the number of times it was streamed. These heuristic approaches, while may be effective on small data sets, they often don't scale. And they tend to worsen the cold start problem, meaning that when new videos come in to the service, they don't really have a lot of sort of click or stream information associated with them. So they tend to fare poorly when compared to the ones that have been around for a longer period. So our approach is basically to use aggregate customer streaming behavior. We're basically looking at not individual customer behavior, but behavior over millions of customers to identify what videos this large set of customers found interesting, and using engagement as a proxy for that. So we use things like the number of streams a video generated, the number of minutes it was watched for, how many days it was watched for, and so on. So basically, popularity is predicted using streams as a proxy. And the way we predict it is we use two components. So we predict the probability that a video would get streamed, as well as the expected number of streams that a video would generate, given that there's a likelihood that it would get streamed. So the assumption here is basically that the more a video gets streamed, the more likely it is a popular video. Now, these models were trained with three types of features. So one being, aggregate sort of engagement signals. This could be streaming, purchase signals, things that I just described, the number of minutes it was watched, the number of days a video was watched, how many customers watched this video, and so on. The features also include metadata. So this could include things like runtime, price of the video, because you're looking at, sort of optimizing across this large swath of content types, right? So it includes that information. Apart from that, there's also date features. And date features we found help identify how new or old a particular video is in the catalog. So this kind of helps capture video newness. So now we trained three ensemble models to predict a smooth probability of stream, as well as the expected number of streams. Now there exists, research that suggests the usefulness of deep learning models to build popularity, as well as recommender models. But the question is that deep learning models, it's about the complexity. So they tend to add to production latencies and sometimes beyond acceptable thresholds. But we want to keep these systems less complex, but at the same time pretty effective, which we found three ensemble models managed to achieve, which was why we chose to sort of use them to solve our problem. Now, these models were basically trained with non-overlapping time windows of data. And what this basically means is the training, validation, and test data sets were collected from non-overlapping or different time periods. The idea is that the training data set is completely blind to any new videos that could have sort of arrived into the validation of the test sets, which happens with trend video because you have a lot of new content that keeps getting released every so often. So this basically tests the ability of these models to generalize well. And one thing I'd like to call out was the impact of age as a feature. Now, as I mentioned earlier, it has been a challenge to sort of boost newer and original content, things that are new to Prime, live sports. And we found that age actually does a pretty good job doing that. So if you look at the chart on the right side, you have age of the title along the x-axis, and you have the predicted score along the y-axis. And you can see that the feature actually boosts newer titles for a short period of time, and then the boost kind of sort of fades away. The idea is newer titles get that initial boost due to the lack of sort of making up for the lack of engagement data. But then after a while, the expectation is that these videos kind of have had enough time that they would have accrued sufficient amount of engagement data to actually determine their true popularity. So to summarize, the models that we tested, they helped increase the number of streams. They increased the number of impressions as well as streaming of new videos that were released within the last 14 days. So I have screenshots of control and treatment from the A/B tests we ran, and in treatment we see some of the new videos, newer at least at the time, getting sort of boosted with the arrows. But the one thing we noticed was these models that were optimized for streams were actually hurting discoverability of purchasable videos, meaning that these were videos that were available for customers to rent or buy on the service. Now, historically, the view has been that we build a generic model, a generic popularity model that would address different types of content. But we've seen that this doesn't often work because customers engage with different types of content differently. And so it's pretty important to factor in content type specific features into models while training popularity models. So in the next round of evaluation, we actually train a specialized model to target a specific video content type. And the goal was to sort of factor in more purchase related features and even optimize for purchase signals to ensure that customers are able to find better quality purchasable videos. And we found that this had a positive impact on sales without actually hurting the streaming metrics. So to conclude, I discussed some of the solutions we use to predict popularity for videos. And that sometimes a one-size-fits-all model may not work, so we'd have to identify alternate optimization strategies to address the requirements for different content types. Of course, we have to keep in mind that these are production systems, so we don't want to increase the total number of models and then make it a maintenance hell. So keeping that sort of thing in mind, identifying only these specialized rankers only where necessary. And the one thing that I noticed was the limitation of our model was that we were not factoring in customers' in-session context in the form of like previous searches, clicks, purchases. This kind of information sort of gives you context about the customer's current streaming intent, if you will. And although we are ranking for, we're providing popular videos, the idea is to make sure that the popular videos we are suggesting to you are in fact relevant to your current streaming session. So that's the direction we want to go in the future. And I'd like to thank my colleagues at Amazon Search, as well as Prime Video Search for their support and feedback. And thank you.
All right. Thank you, Lakshmi. That was a very interesting talk. We have actually quite a few questions from the audience. And let's get started with one about the number of streams versus the number of users that stream a video. Do you just consider the number of streams as a standing feature for a video? And the total number of like unique users, that's roughly the same?
Is the question, what are we predicting? I don't think I got the question.
The question is if the number of the streams is really a standing metric for the number of users.
I guess you could approximate it to that, but that's often not true. I mean, the number of streams tends to be way more than the number. So they may be correlated for sure, but they're not. It's probably not a standard for the number of customers, I don't think. Yeah.
So do you use the number of customers? Do you use that as a different feature?
We identify how many customers streamed a particular video. We definitely have that information, so that gives you a sense of that's another sort of dimension. Yeah, but I guess in a sense it helps predict. Exactly. Yeah.
And then how do you calculate the truth of probability of T?
We get it. We collect it from the logs, right? So we know how many times a particular video was impressed and how many times it was streamed. So that kind of tells you, it gives you that.
I think that was just a clarification question.
Okay. Got it.
Maybe it's the probability, but you just calculate that estimate, right?
Yeah.
Do you consider a customer cohort feature? Like if you have different countries or different, do you have different models for the language for country, since Amazon Music is worldwide?
Yeah. That's an excellent question. Actually, right now we don't have that in our models, but that's definitely something we want to factor in. We want to maintain that popularity is still something that's. I mean, be true to the definition of popularity, I guess, meaning that it's something that's popular in across a large number of customers. But I guess in terms of like making it sort of relevant to, let's say, a set of customers who are interested in action drama movies, or having like some sense of like genre representation, and then making popular recommending popular videos that are relevant in that particular genre. So I can see how there is a way to sort of contextualize with that information, and that's something we want to try going forward and factoring in as features. So there's different ways of implementing that. So you could either have it as features, or you could even have your own sort of specialized models to address specific sort of groups if they're large enough, and if your models can't really address specific sort of like popularity requirements, I guess.
Okay, sounds good. Last question is, do you detrend the data in a specific way, given that tree models do not perform well when dealing with trends? Distinct time window or for training and test. Do you deal with that out of the box?
So the features themselves are not temporal, so they're not time dependent. Mm-hmm. Yeah, so we don't apply any detrending to remove any form of like seasonality from the data. But we do have like these feature models that actually generate other features which tend to be temporal. So in that case, we do some amount of detrending. That's not a part of this particular work, but that's different work. But not for this model, because the features themselves are not really temporal in nature.
That makes sense. All right, thank you very much, Lakshmi.
Thank you.
That was great. It's always good to have papers mixed with industry talk and to see all the stuff going on. Okay, so let's go to our last talk, and it's Zach Schendel from Netflix, and he's going to talk about human perspective on algorithmic similarity.
Can you hear me?
Yes.
All right. Hi, my name is Zach Schendel, and I work on the consumer insights team at Netflix within product innovation. And today I'm going to be talking about a human perspective on algorithmic similarity. I did this project in collaboration with Faraz Farzan and Siddhi Sundar. So I'm going to start with a quick story. Even though this particular title, I Don't Feel at Home in This World Anymore, was recommended to me often by Netflix, highly recommended. It showed up on my page multiple times. I rejected it almost every time. And when I looked at it on Netflix, it just didn't look that good or sound that good. I watched the trailer, just wasn't that interested in it. One thing that I like to do in order to determine whether I'm going to be interested or not in a title is to go to a section called More Like This, which is found behind every title. And you can look for titles that Netflix thinks are similar to the source title in order to get a sense of what it might be like. When I saw the recommendations in the More Like This section for this title, they didn't make a whole lot of sense to me. I didn't really understand what the connection was between them, and it didn't really help sell me on it. Ultimately, the thing that did help sell me on it was stuff off of Netflix. So reading about it on the internet, seeing that it won an award, finding out that it was done by people that had done other movies that I liked in the past, and I did end up watching it, and I really enjoyed it. But if I were to personalize More Like This for myself, these are the titles that I would have included in the list. There's a couple here that are created by the same sort of talent. There's a couple that have similar genre themes and a couple that have similar actors. And this would have put it over the top for me. I would have definitely watched it. So I wondered, am I the only one? And a quick Twitter search made me realize I wasn't the only one. Here's a good tweet for you. The row in my Netflix labeled "Because You Watched Russian Doll" covers so many genres that I think the algorithm said, hey, we noticed you watched an audiovisual entertainment. Did you know these are other audiovisual entertainments? So there's a series of these. You can go and search them on Twitter if you'd like, but these and other examples got us thinking, like, what exactly is similarity? How do you define similarity? And where really is the line between something being deemed perceptually similar and perceptually dissimilar? So we decided to ask our Netflix members. We used 3 different research methods in the project. The first was an international landscape assessment of the concept of similarity, both inside the category. That means among Netflix users or users of other streaming services or other e-commerce sites, as well as outside the category, even going to physical locations like a Target or a grocery store and seeing how things might be grouped together. The second thing we did was we did a series of qualitative interviews with Netflix members where we just went through their page of recommendations and asked them for each canvas in which we're recommending similar titles, whether they thought the recommendations were appropriate or not, essentially. And the last thing we did, I'll talk about more later, but it was using a method called inverse multidimensional scaling, which allowed us to do a quantitative evaluation of perceived similarity. Okay, so the overall answer is it's really complicated, but we can actually help our recommendations. And so we're gonna unpack 3 sources of complexity today. The first is the placement. So where in the user interface is the recommendation found? The second is the person who is seeing the recommendation, what's their past experience with that source title? And the third is the context. So what else is going on in the moment and what are the user's needs? So let's start with the placement. Where are the recommendations placed within the Netflix UI? There's actually multiple places in the Netflix UI that are populated using algorithms that use some kind of dimension of similarity. So on the left, you can see what a more like this section. After you watch Stranger Things, we recommend something, or while you're watching something like Stranger Things, we recommend more like this beyond Stranger Things. There's rows called because you watched whatever. Here's some things that you should watch. And then after you finish a title, in this case, The Kissing Booth, we will recommend another title to you, in this case, To All the Boys I've Loved Before. We found that members had higher expectations of similarity when they were part of a one-to-one recommendation. So the one I just explained to you, you finish a romantic teen drama called The Kissing Booth, we recommend another romantic teen drama called To All the Boys I Loved Before. The connection between those makes complete sense if you know anything about those movies. But there are other instances, and I'm showing you an example on the right, where we're recommending a title called The Office, which I'm sure a lot of you have seen, the US version, because of your interest in The Crown, which is a dramatized version of Queen Elizabeth's entire life, ruling. Those 2 titles have very little in common, and it doesn't really make sense to recommend The Office based on your interest in The Crown. So in both of these cases, you're taking a risk with a one-to-one recommendation. You don't really have another backup option. There's no other titles to help explain what might be the connection between the source and the recommendation. How on the opposite side, you have one-to-many recommendations. There's actually much lower expectations in places like this. Let's look at this row. So because you watched $1 Million Beach House, we recommend this entire row of content. When you look at the titles, you see that they all have a common theme. They're all reality shows. And just like $1 Million Beach House, which is another reality show, right? But if you think of this as a one-to-one recommendation, because you watch $1 Million Beach House, then you would recommend Queer Eye. The connection isn't great. Like $1 Million Beach House doesn't really have to do with human renovation. It has to do with house renovation work. They do share a common genre, and that really comes out when you see the multiple recommendations. Another place where people have higher recommendations is when those recommendations come after some sort of interaction or some sort of explicit entry. So, for example, if you search for something, if you search for Stranger Things, you do expect to get Stranger Things back, but you also, in case you've already seen it and you're searching for things like Stranger Things, you would expect to see things like Beyond Stranger Things or other titles. And also, as I explained earlier, you can go into a title and click more like this and see things that are similar. People, when you go through these, when you jump through these hoops, when you type things in, you go to search, when you do these extra steps, you expect to see more similar recommendations than you would in a generic page of recommendations while just browsing around. So to summarize, not all canvases are created equal, especially when you get to one-to-one recommendation canvases and you compare those to one-to-many recommendation canvases. The second source of complexity that we found is the person. So who's watching the title, or who you're recommending the title to, and what is their personal past experience with the source. To do this, we did a method called inverse multidimensional scaling. And what we asked people to do is we gave them a source title in the center of the screen, and we asked them to drag over into the screen something that you can see the example right here, about 8 or 9 titles. And we said, just put the titles that are closest in your mind, the most similar in your mind, closest to other titles that might be related to it. And you can put them anywhere on the screen. And then after, hundreds or thousands of people, you can look for the actual distances in the screen and how likely they are to be clustered together with one another to understand perceptual similarity between the source title and all the other recommendations. We also asked people to put a word to it or put a couple words to it to describe why you think these titles go together. So let's walk through an example to illustrate what we learned. A title like Stranger Things is really multidimensional. It has multiple genres like sci-fi, fantasy, horror, comedy-ish. There's some tones to it, like, it's a nostalgic, it's scary, it's exciting. It references the 80s. It stars some famous people like Winona Ryder, etc. And all of these sorts of things might be interesting to some people or many people. But when you look for similar titles, classically similar titles, where you would expect a lot of the same tags to show up, a lot of the same overlap, it's a kind of a short list. I put 4 here just to give you an example. All of these shows sort of have ensemble casts of teenagers set kind of in the 80s on some adventure, and maybe they're fighting some evil thing or monster. Maybe there's a supernatural element to it. But you quickly run out of options if your expectations are sky high for similarity. These kind of recommendations would work best in a one-to-one situation. In order to fill out the bulk of similar recommendations, you have to focus on both broad and specific drivers of perceived similarity. And we'll go through each of those. So broad similarity drivers are mostly surface level things like genre. And so, Stranger Things is a sci-fi. Here's another sci-fi that you might like. Those are kind of generic. They kind of pique interest in a title. They do have clear source links. It's obvious that the two have the same genre, but that doesn't actually mean you're interested in watching the recommendation just because it has the same genre. Specific similarity drivers were much more varied and difficult to predict, but were way more likely to drive you into a final choice of, I should watch that. So for example, if that particular individual did watch Stranger Things and you find out that they are into Winona Ryder movies, you might then recommend another Winona Ryder movie. But other individuals might really glom onto the 80s nostalgia or the monster fights or the group of misfit teens in the 80s, etc. These are much more difficult to predict, but these are the things that get people most excited about watching something. They're very high risk, high reward situations where trust busters can often occur. And what we define as a trust buster is we're going to recommend this title because of you're interested in this title. If the link between the two of them is completely wrong or totally unclear, people stop believing that our recommendations are good and that we're doing some sort of benefit for them. So to summarize the second one, the degree to which something is similar or is not similar really is in the eye of the beholder. People will latch on to different things that are exciting about that title. And for things that are multidimensional, you have to think about broad and specific drivers of similarity and where to emphasize each of those in order to minimize trust busters. And the third thing we'll talk about is the context. So what is going on and what are the user needs? To add even more complexity to the story, even if you hold the location or placement within the UI of the recommendation, as well as the person you're recommending to, context also matters. So after you finish a show, like I explained earlier, like the kissing booth, we'll recommend something else to you, like To All the Boys I've Loved Before. Okay, you are likely to watch something that is similar. So after you finish Queer Eye, you are likely to watch something like Next in Fashion, which is another reality show. However, that is not actually the most common path. For example, after you finish a reality show, 18% of members go on to watch another reality show. And so the other 82% of members don't actually watch something that's even within the same genre. And half of members stick with the unserialized content. Half of members stick with Netflix originals, but you can see that there is a whole host of people that are not choosing to go down the exact same path that they're on. And there's a lot of reasons for that, and most of these are driven by context, where in some cases, similarity is actually unnecessary and the opposite of ideal. For example, you may just want to rewatch something familiar you've seen before, or that was too intense, I want to watch something that's a change of pace, or I don't have time for another long movie, I just want to put on something short. So to summarize context further impacts the complexity, because you have to think about, like, this kind of person, are they likely to do a more of a change of pace recommendation, or do they like sticking with something similar, and all the steps in between. So in the end, the research validated a new similarity model, and after putting it through our method that I explained earlier, we found that there were quite a few lower % of trust busters in the new model compared to the old model. And this new model increased engagement with our similars across some canvases. And for me, at least, now I get better recommendations in my More Like This. And that's it. I'd like to open up to questions.
Thank you, Zach. Super interesting. Even listening to it for the second time. Okay, so let's go to questions. The first one is no doubt the balance of complexity and your insight. So the question is, how is the human perspective of algorithmic similarity balanced against the increasing complexity in models that derive latent variables and that are really not so interpretable?
Yeah, I think they can work together. I think the key is that you shouldn't assume that just because you created a similarity model that you should use it in every place that similarity models could be used. You might find that it works better on a home page than it does in a search context. You could try out different models in different contexts and see which ones actually work. Whether they're deriving some sort of different latent variables in either case is somewhat irrelevant. I think the idea is that you don't assume that it will work in every single context equally well for every person.
Okay. And the second question is you talked about the expectations. What is the consequence of high expectation? Is it, what do you observe as the metric or data as to quantify things like a high expectation?
Yeah, so I mean, one thing that would probably be fairly obvious is if you trick somebody into trying something because you have made it seem like something that they really liked, then they will be upset that they wasted their time on that. And you think of that as like a false positive, I guess. On the opposite side, you have incorrect rejections, where someone actually would have really liked to watch this, but the way that you've described it to them either makes no sense or isn't actually describing it the way that would be relevant to them. So you as a company, of course, like miss out on the engagement, but more so like the member misses out on the joy of watching something amazing that they can tell their friends about and talk about, and then get more value out of the service. And both of those things matter a lot. The other problem that you sometimes run into is that you can potentially be be just offensive sometimes in the way that you describe something, and those are things that we care a lot about. We want to be true to the title, and we want to like really explain the story and be objective about what it's going to be like, so people can make really smart choices to watch or not to watch.
So then in your observation, what is the observed metric of high expectation? Is it high click probability, or is it low click probability? Or is it just you think because you're explaining in some ways they're categorized, those explanations are categorized as inducing high expectation?
Yeah, that's a good question. It's not something necessarily that we've perfected, but if you give people evidence that says, because of your interest in this particular title, you will like this particular title. And those are things that we call, let's say, necessarily high expectations. Mm-hmm. That will put people over the top, because it's almost like you're talking to someone and you're making a recommendation. The likelihood that you play something in that scenario is much higher than the likelihood of, because you watch this, here's a row of 75 titles that may be somewhat related to it. The link between those isn't as strong, so you don't feel as drawn to making one of those 75 choices as you might a single one-to-one recommendation, right? So you have to be really careful with those. In fact, we've scaled back a lot on those one-to-one recommendations, because you can run into potential issues.
Got it. That makes sense. Sorry about that. My son just barged in for some reason. Okay. Let me see if there is another question. I am not seeing any more questions. And then I think that's it. I think that concludes our session this tonight or morning, wherever you are. And let's thank all the speakers again. I'm going to clap on behalf of all the attendees. Thank you so much for doing this one more time, and to keep the whole RecSys more interactive experience, even though that might mean you're staying up for one or the other. So thanks again, and we'll see you in the next session.
Thank you. Thanks.